Muscle is probably the most iconic organ in your body. No other organ gets its own holiday or as much radio play, and you're unlikely to get a love note decorated with a kidney or a spleen or even a brain, which is really what rules the emotions. Don't get me wrong, the heart does some great things. Namely, it powers the entire circulatory system, transporting nutrients, oxygen, waste, heat, hormones, and immune cells throughout the body over and over. But in the end, the heart does not make you love, it doesn't break apart if you get dumped by your boo, and it's not a lonely hunter. The truth is, the heart is really just a pump. A big, wet, muscly brute of a pump. And it doesn't care about poetry or chocolate or why you're crying. The heart has only one concern: maintaining pressure. If you've ever squeezed the trigger on a squirt gun or opened a can of shaken soda, you've seen how fluids flow from areas of high pressure, like inside the gun or the can, to areas of low pressure, like outside. The heart's entire purpose is to maintain that same kind of pressure gradient by generating high hydrostatic pressure to pump blood out of the heart while also creating low pressure to bring it back in. That gradient of force is what we mean when we talk about blood pressure. It's basically a measure of the amount of strain your arteries feel as your heart moves your blood around. More than 5 liters of it at about 60 beats per minute. That's about 100,000 beats a day, 35 million a year, 2 to 3 billion heartbeats in a lifetime. The basic physiology of which you can easily feel just by taking your own pulse. I don't have a watch. Now that might not inspire so much poetry, but it turns out it's still a pretty good story. Let us begin with a little anatomy. Unless you happen to be of the Grinch persuasion, the average adult human heart is about the size of 2 fists clasped together. One of the few bits of trivia you often hear about human anatomy that is actually true. The heart is hollow, vaguely cone-shaped, and weighs only about 250 to 350 grams, a pretty modest size for your body's greatest workhorse. And although Americans tend to put their right hand over their left breast while pledging allegiance, the heart is actually situated pretty much in the center of your chest, snuggled in the mediastinum cavity between your lungs. It sits at an angle though, with one end pointing inferiorly toward the left hip and the other toward the right shoulder, so most of its mass rests just a little bit left of the mid-sternal line. The heart is nestled in a double-walled sac called the pericardium. The tough outer layer, or fibrous pericardium, is made of dense connective tissue and helps protect the heart while anchoring it to some of the surrounding structures, so it doesn't bounce all over the place while it's beating. Meanwhile, the inner serous pericardium consists of an inner visceral layer, or epicardium, which is actually part of the heart wall, and an outer parietal layer. These two layers are separated by a thick film of fluid that acts like a natural lubricant, providing a slippery environment for the heart to move around in so it doesn't create friction as it beats. The wall of the heart itself is made of yet more layers, 3 of them. That epicardium on the outside, the myocardium in the middle, which is mainly composed of cardiac muscle tissue that does all the work of contracting, and the innermost endocardium, a thin white layer of squamous epithelial tissue. Deeper inside, the heart has a whole lot of moving pieces that I'm not going to pick apart here, because the really big thing to understand is how the general system of chambers and valves and veins and arteries all work together to circulate blood around your body. Of course, fluid likes to move from areas of high pressure to areas of low pressure, and the heart creates those pressures. Form, once again, following function. Your heart is divided laterally into 2 sides by a thin inner partition called the septum. This division creates 4 chambers, 2 superior atria, which are the low pressure areas, and 2 inferior ventricles that produce the high pressures. Each chamber has a corresponding valve, which acts like a bouncer at a club at closing time, like he'll let you out, but not back in. When a valve opens, blood flows in one direction into the next chamber, and when it closes, that's it. No blood can just flow back into the chamber it just left. So if you put your ear against someone's chest, and yeah, ask for permission first, you'll hear that lub-dub. Lub-dub. What you're really hearing are the person's heart valves opening and closing. It's a relatively simple but quite elegant setup, really. Functionally, those atria are the receiving chambers for the blood coming back to the heart after circulating through the body. The ventricles, meanwhile, are the discharging chambers that push the blood back out of the heart. As a result, the atria are pretty thin-walled because the blood flows back into the heart under low pressure, and all those atria have to do is push it down into the relaxed ventricles, which doesn't take a whole lot of effort. The ventricles are beastly by comparison. They're the true pumps of the heart, and they need big, strong walls to shoot blood back out of the heart with every contraction. And the whole thing is connected to the rest of your circulatory system by way of arteries and veins. We'll go into a whole lot more detail about these later, but the thing to remember first, if you don't already remember it, is that arteries carry blood away from the heart, and veins carry it back toward the heart. To differentiate the two, anatomy diagrams typically depict arteries in red, while veins are drawn in blue, which incidentally is part of what has led to the common misconception misconception that your blood is actually blue at some point, but it isn't. It is always red. It's just a brighter red when there's oxygen in it. So let's look at how all this comes together, starting with a big burst of blood flowing out of your heart. The right ventricle pumps blood through the pulmonary semilunar valve into the pulmonary trunk, which is just a big vessel that splits to form the left and right pulmonary arteries. From there, and this is the only time in your body where deoxygenated blood goes through an artery, the blood goes straight through the pulmonary artery into the lungs where it can pick up oxygen. It finds its way into very small, thin-walled capillaries, which allow materials to move in and out of the bloodstream. In the case of the lungs, oxygen moves in and carbon dioxide moves out. The blood then circles back to the heart by way of 4 pulmonary veins, where it keeps moving to the area of lowest pressure, because that is what fluids do, and in this case, that's the inside of the relaxed left atrium. Then the atrium contracts, which increases the pressure, so the blood passes down through the mitral valve into the left ventricle. So the thing that just happened here, where a wave of blood was pumped from the right ventricle to the lungs and then followed the lowest pressure back to the left atrium, there's a name for that. It is the pulmonary circulation loop. It's how your blood unloads its burden of carbon dioxide into the lungs and trades it in for a batch of fresh oxygen. It's short, it's simple, at least in the way I have time to describe it, and it's just delightfully effective. Of all the substances you need to continue existing, oxygen is the most urgent, the one without which you will die in minutes instead of hours or days or weeks. But it's pretty useless unless the oxygen can actually reach your cells, and that hasn't happened yet. For that, your newly oxygenated blood needs to travel through the rest of your organ systems and share the wealth. And that fantastic journey, known as the systemic loop, begins in the left ventricle when it flexes to increase pressure. Now, the blood would like to flow into the nice low-pressure left atrium where it just came from, but the mitral valve slams shut, forcing it through the aortic semilunar valve into your body's largest artery, nearly as big around as a garden hose, the aorta, which sends it to the rest of your body. And after all your various greedy muscles and neurons and organs and the heart itself have had their oxygen feast at the capillary bed buffet, that now oxygen-poor blood loops back to the heart, entering through the big superior and inferior vena cava veins straight into the right atrium. And when the right atrium contracts, the blood passes through the tricuspid valve into the relaxed right ventricle and right back to where we started. This whole double loop cycle plays out like a giant figure 8, heart to lung to heart to body to heart again, and runs off that constant high pressure, low pressure gradient exchange regulated by the heart valves. So the first lub that you hear in that lub-dub is made by the mitral and tricuspid valves closing. And they do that because your ventricles contract to build up pressure and pump blood out of the heart. This high pressure caused by ventricular contraction is called systole. Now, the dub sound. And just to be clear, I'm not talking about dubstep sounds. That's the aortic and pulmonary semilunar valves closing at the start of diastole. That's when the ventricles relax to receive the next volume of blood from the atria. When those valves close, the high pressure blood that's leaving the heart tries to rush back in, but runs into the valves. So you know when you get your blood pressure measured and the nurse gives you 2 numbers, like 120/80. The first number is your systolic blood pressure, essentially the peak pressure produced by the contracting ventricles that push blood out to all your tissues. The second reading is your diastolic blood pressure, which is the pressure in your arteries when the ventricles are relaxed. These 2 numbers give your nurse a sense of how your arteries and ventricles are doing when they're experiencing both high pressure, the systolic, and low pressure, the diastolic. So if your systolic blood pressure is too low, that could mean that, say, the volume of your blood is too low, like maybe you've lost a lot of blood or you're dehydrated. And if your diastolic is too high, that could mean that your blood pressure is high even when it's supposed to be lower. Considering how much we've talked about the importance of homeostasis, it should come as no surprise that blood pressure that's too high or too low, or anything that affects your blood's ability to move oxygen around, can be dangerous. Prolonged high blood pressure can damage arterial walls, mess with your circulation, and ultimately endanger your heart, your lungs, brain, kidneys, and nearly every part of you. So I guess you could say that the best way to break a heart is to mess with its pressure. But good luck trying to write a song about that. Today you learned how the heart's ventricles, atria, and valves create a pump that maintains both high and low pressure to circulate blood from the heart to the body through your arteries and bring it back